So now we come back to today's, to continue with the things we were doing last time. Some of it, let us restate the abstract things, and then these two lectures are quite nice, so I hope to rely on them. Okay, so now the title for today's lecture is Representations Characters and Applications to Spectroscopy. We will use, okay, so so to just recap somewhat what we were doing last time. We have the orthogonality theorem. Great or wonderful or whatever it is called. So let us write once the orthogonality theorem in its most general form, based on which, for deriving which Schur proved his lemma. So sum over all G belonging to G. Suppose we have a representation D alpha G, and we have another representation D beta, and we will take star. We will assume unitary representation because we have proved that you can always find a unitary representation, and IL and JM. So this has orthogonality in each of the three class of indices. So it is size of G, number of elements in the size of the representation alpha, and times delta Ij, delta Lm, and delta alpha beta. So this is the great one. Indeed, it deserves that name. So this is size of irrep. So this is for irreps, of course, irrep alpha. So the theorem, of course, applies to irreducible representations. And then the derived ones from this, and we use unitary reps. And from this we derived the related relation for characters. Chi alpha G, we have the relation sum over G but then we know that the characters are same for all the elements in a class, and we will soon see the geometric. We have already discussed the geometric meaning of a class. They are essentially elements that do the same thing, but their starting points are different, that's all. So, since chi alpha are same within a class, conjugacy class, it also, we can also write this out as Pi, where this is the number of members in the class I, and now we do not sum over G anymore. So, this summation was over G, but now we simply sum over classes. I index is class, Pi, chi I, so sorry, I index is the class actually. Right. Okay. Then we learned from this that we could in fact then for a reducible representation which we just called D, such that D is direct sum in linear algebra sense of some standard way of listing irreducible representations, which we sometimes write symbolically as sum over alpha equal to 1 to rho, where rho is the total number of irreducible representations. We write this out as equal to m alpha times d alpha G, and rho is total number of irreps. Distinct irreps, of course. Right. So, from this we can deduce that the weightage m alpha of an irrep alpha in D can be extracted by using the orthogonality. Take the characters in the representation D, whatever it is, and then multiply it by chi star, project it out onto the representation alpha, and sum over all G. That gives the weightage of the representation alpha in it. We also had proved that there is another kind of orthogonality relation and this is for so look at this, we have been writing chi I alpha and chi beta j chi beta I, and then summing over I to get delta alpha beta, but you can also do this and sum over alpha equal to 1 to rho, sum over all the irreps, not over the classes, and that produces again the size of G divided by the Pi, the number of members in the class I, times delta Ij. So that we had here. It's called order of the class actually. Class I. The order of class I is Pi. Then we have another kind of orthogonality where we also get this. The upshot of all this is that we have very strong constraints on the number of classes we can have and the number of irreps we can have. And then there is a clever construct called the regular representation. Where G acts upon itself as permutations. So, dimension of the carrier space, what is the carrier space? Somebody said, right? G itself, G is acting on itself. So, the carrier space on which G is realized is G itself. So, it is obviously a G dimensional representation. So, G dem representation, i.e. again I want to emphasize G by G matrices. When somebody says irrep of size n, it means n by n size matrices. Now, one thing we learnt was that in the regular representation, identity is the only one that has non-zero characters. And so, I will not repeat all this, but using this one can prove, we proved that sum over n alpha, which is the dimension n alpha squared, is equal to G, where n alpha is the dimension of the irrep alpha. So, some square of the dimensions has to add up to G. So, this is going to restrict number of classes and number of representations. Not only that, we had seen that the number of times a particular representation is contained in this regular representation is exactly equal to the size of that representation. So, you can see last time's lecture and we had proved all this. Now, today I want to take up uses of this in chemistry, and I could have done this myself, but I find some really nice slides on the internet. So, I just decided to, where to write, maybe I do not write over here, but we will use it will be in the recorded lecture, and I have linked these two slides on our Moodle page. So, you can read them also of the earlier one of Carsten Horn. So, this is somehow he does not, this is actually some introductory course in chemistry. So, of course, the slide starts nicely by telling you what is a matrix, that is nice, but then it quickly goes into complexity, saying that if you have some a molecule like this, he is going to consider three-dimensional case. So, in the quiz we just gave this ellipse in the plane and just worried about its transformations within the plane, but once you have a molecule, although the molecule is planar, there is the z direction because the atoms are not actually points. So, if you just make an idealized figure which is planar, then it's fine. Such molecules are called planar, but indeed you can flip the z-axis and it has a meaning because the atoms are some fluffy things which go upside down. So for this, these elements are identified. E, which is identity, C2 is just because there are bromines hanging here, you can only do 180 rotation. Then there is a full space inversion, which is all sending x to minus x, y to minus y, z to minus z. And finally, there is sigma h. This is what we would not consider if we have an idealized planar figure. But here, if you ran the plane in the plane of the molecule, there is a reflection symmetry about that. So there is a z axis, z go to minus z is a separate symmetry. Using this, C2 is identified. So there is x, y and z axes. So the C2 is just 180 rotation, so it is -1, -1, this is 1. And this is inversion, minus, minus, minus. Now, points out what are characters, okay, and that there is they obey group law. But let us look at the bottom table. Here he has considered the, right, we should read this row carefully. Here is a particular representation that is being presented. Identity is of course 1, 1, 1. C2 is where x and y are exchanged because it's a 180 rotation. Then there is full space inversion, and then there is a z-axis reflection, the sigma h plane. Okay. These together form a group, and you can check because C squared gives identity, sigma h squared will give identity, and so on. So for this particular 3 by 3 representation, if we begin to write the characters, then for the identity we will write 3. For the C2 we will get a -1 because it's a trace of this. For the inversion we get -3, and for the reflection plane we get 1. Okay. Now this gamma is reducible, and one of the ways of seeing it is that after all it is just 1, 1, 1 dimensional. So it is block diagonal, with each block just containing one element. So this is clearly a reducible representation, and that's what is identified. Essentially, each of the axes is treated more or less independently. So this square bracket identifies a single representation in this, and we can write out the character table of this by now there is a notation of these B, B and A which will be explained soon. We already saw, so this is actually guesswork and we are going back and forth a little bit. Just to repeat, we know that this is an abelian group. So every element is in its own conjugacy class, right? And so there are 4 conjugacy classes. Correspondingly, we know there should be 4 independent irreps, right? There are as many conjugacy classes as there are irreps. But the way we are breaking up this representation, we are getting only 3 of them. But whatever they are, we are writing them down. So 1, -1, -1, 1, 1, -1, -1, 1. Then the second row is 1, -1, -1, 1, etc. So these are just writing these out and showing how the reducible rep is just composed of this. Each of these occurs once in it. The M alpha that we were deriving is only 1 in this case. Mind you, this is a very, very simple example, but don't be fooled by it because it gets complicated very quickly. So this is written out. Characters show each irrep and how it transforms, and points out that this is the other thing from chemistry and from physical point of view. This row essentially captures property of x coordinate, this row captures property of y coordinate. And the other thing is that if this particular axis x, what is its fate under each of the elements that you have to see. and if nothing happens to it, then we get a character 1, and if it gets flipped, then we get a character -1, and if it is neither, then we get actually 0. Okay, if it is not a definite, that is the rule about characters. So you will see how chemists work this out. They are not going to worry about Schur's lemma. Okay, so they just figure out from here that, oh, you just assign character 0 if nothing happens to it. Now in this case, each of the elements of course does touch these symmetrically or anti-symmetrically. So this is what happens for, and now he has introduced one more representation. So here it's explained, the AU transforms, like the lowest one transforms essentially like z-axis, the others don't. So the things that don't change, we get 1, the things get flipped, we get -1. If actually it neither was symmetric nor anti-symmetric, then we would have to put entry 0. Now, so AU has the same symmetry as Z in C2H, and the two BU representations are exactly the same, and we can quote merge them. So they actually reduce to only one particular representation. This is because C2 is it's a the two are in the same conjugacy class, so they are not giving anything new. So X and Y, these are merged. So this is called BU, and this is the Z one is called AU. This terminology is A, B and E, and we are not going to really worry about it, but you will see it listed all the time. What is interesting to worry about is the fate of which coordinates are covered by this particular representation, and fate of this is captured by this representation. Now, but we know that we do need 2 more rows here, and list of complete irreps. So here, in addition to AU and BU, 2 new things are added, AG and BG. The AG is the trivial representation. Everything is represented by just 1. Remember that the trivial rep is always one of the irreps, and that's a very important thing to remember. And then this, you may ask, where the hell did BG come from? And even if you knew no geometry or visualization, we can get it by orthogonality, because I know there are 4 classes. I have 3 representations in hand already. I have to guess the 4th one. Well, it has to be a choice of +1s and -1s such that it is orthogonal with each of the other 3. So automatically we get these signs, because right, if you just work it out, it will come out like that. So I don't want to be reading this transparency too closely, because we'll get carried away. I do want to, so this point number 4, this subscript U and G has essentially German word origin. For point groups with inversion, the representations are labeled with a subscript G, which means Gerard, or U, which means ungerard, to denote symmetric or anti-symmetric with respect to inversion. So whatever that is, I will not elaborate on it further, but that is the way of, that is the nomenclature used. So now the more important thing from chemistry or physics point of view are that he has added these 2 columns. So first one was, we already had this AU and BU, and they were properties of Z, X and Y. But these 2 are also properties of rotations, okay, Rx, Rz and Rx, Ry. So identity, the trivial representation is property of rotations about Z axis, whereas rotations about Rx and Ry themselves get affected by this element B. So they are here. They share essentially what happens to the XZ plane and to the YZ plane. So Rx, if you rotate about X axis, you rotate Y and Z, so that is this YZ, or you rotate about Y axis, which means you rotate X into Z. So there are these quadratics of the coordinate values, which so these new classes that we got, the new irreps we got were such that they have specific property with respect to the quadratic things. Particularly the identity leaves, the trivial one leaves x squared, y squared, z squared, and the product xy individually invariant, whereas the xy plane, yz plane is left invariant by this second class of irrep. And there is a direct correspondence of rz, then you get xy, z, xy, x, yz, and yzx. This will be important a little bit later. So, and this is how they simply read off. Chemists just read off by looking at a molecule what the character table is, and by guesswork and by orthogonality figure out the whole table. So, the last two columns give functions with origins at the inversion center that belong to the given representation. So, for example, this is some typo, actually it means dx squared y squared, or this is the d orbital, x squared y squared and dz square orbitals are ag, and the pz orbital belongs to au. So, this is p and these are higher level, the d. Okay. Now, is coming back to actually emphasize what we just did, the tricks we played, and also, yeah, is just checking without proof the results we have proved, and we have proved this sum over all I chi I squared will be equal to h. But there is also another interesting result, which is that sum over r. We proved a preliminary version of this, but not this particular result. We did prove that sum over all alpha gives you delta I chi, delta ij. So, if you take square of that, then you will actually get this result. Here h is the order of the whole group. Okay. So, he is just verifying that if you take any particular, so chi of the identity element, chi squared, sum of these has to equal 1, and sum over all the irreps, so running like this, I am sorry, so sum over for a particular I, fixed value of the, no, it's which way is it running? So, there I labels irreps, notation change. So, there is a I labels irreps, and so that orthogonality property is basically verified here. And he also points out, which we already noted, that this one, so the bottom two were already guessed first, I mean they occurred naturally, you wrote a 3D representation and these two occurred there. We already know that the trivial one has to be there, and he is asking how do you get the middle ones, and do you get them by orthogonality. So, that is what he is proving, and happy that it can be done. Okay, good. So, now we come to a more interesting example. The previous one simply had only 1D representations, but now we also have a 2D representation. So, it is just 1 degree more complicated, and this is going to be C3V. C3V means 3-4 rotations and vertical axes of reflection, vertical planes. So, the V are the planes that contain the axis of rotation. So, that is so a V axis, the V plane that contains the nitrogen and one of the hydrogens at a time, you have a reflection symmetry. Now, in this case, again you can begin with the quote organic representation that you would think of by writing a 3×3 matrix. You would have the C3, there will be two C3 elements because 120 and 240 degree rotation. So, they would have this form cos theta sin theta, which for 120 just boils down to this matrix. And then we also have the vertical axis, let us say, which contains the x and z plane, then it changes the sign only of y. Okay. So, these are firstly noted as properties of specific element. So, there are two different rotations about the z-axis, but they both belong to same conjugacy class, because each of them is just carrying out 120 rotation relative to the previous thing. So they can be related by a conjugacy relation. They would belong to the same class. Similarly, the three reflection planes are all doing geometrically the same thing. It's just that it is this plane or that plane. And in fact, a rotation, the z-axis rotation, can rotate the planes into each other. So they all belong to the same class. So we write the class name by this geometric suggestive thing and the number of elements in it. C3 is a threefold rotation, 2 pi by 3 rotation, but there are two of those. So we just bother to list only the classes and not the whole group. The whole group will have 6 elements, but we write only the classes directly. And here he has taken only one member of the representative identity. This C3 rotation, we took only the 120, not the 240, and the character is 0. And this one will have character, this one will have character plus 1. Okay. We have to come back to this. So by the way, there is a slight ambiguity. The E, this author has used capital E to denote the identity element, but capital E is also used by chemists in the old German notation, the G and U, there is also a thing called E. So the irrep is also called E for some reason. Okay. But now he points out that this generic 3D representation that we could think of is obviously reducible, right? Because it has 2 by 2 blocks and it has a 1 by 1 block of the z-axis. So it is a reducible representation. Is that clear? And so here shown by drawing this red matrix delimiters around the upper matrix and then green thing lower. But the 2 by 2 cannot be reduced any further because the operations are mixing x and y planes, so x and y axes. So there is no way to reduce it any further. And therefore draws up the character table. The third representation he finds by orthogonality. So these two, A1 and E, are over here already. A1 is the green box, basically is the lower one that split off, and it was actually trivial, nothing happens to the z-axis. So it is 1, 1, 1, 1, 1. And this one will be called A1. But there are only 3 conjugacy classes, so there is a middle row to be filled. You can get it by orthogonality because you just have to multiply this with this, this with. So you will get 3 relations which will determine the 3 coordinates. So that's what he says here. The third representation can be found by orthogonality and the fact that the chi of E is equal to 1, that it is a one-dimensional representation. Okay. So additionally says try proving that this character table actually has the properties expected of a character table, but that property is actually orthogonality, but you can check the column wise orthogonality as well. But what is important to note also is that the class A1 and A2, A1 affects the under A1 the property of Z and property of x square, y square, z square is captured. Under A2, which we had to introduce by hand, essentially captures the RZ, which I would think captures the xy plane. But that is not true. So the E, third one, where the character of identity is 2 and this is the character of this rotations minus half plus minus half is minus 1 and 3 is 0, because as you remember, if the element that you are considering has a definite property, that we get a minus sign. If the element being considered as no definite property, then we get 0. So each molecule has a point group, and you can go down decision tree. That tree is there in that K horns thing. Okay, and first part therefore is to identify character tables. Okay, so this is end of this part, which is quick and rough way of identifying building up character tables.